Hey guys, I'm Sanjeev from searching.com and welcome to another presentation on signal reconstruction and optimization approach. Okay, the area is optimization and specific order reconstruction. Okay, in this video I'm going to show you how you can reconstruct your signal or denoise your signal, provided you want to preserve the specific features or specific properties of a signal, that is any sharp transition or human voice, etc. Okay, so let us begin. So consider this is an audio signal and let me show you what it sounds like. Hello, I am Sanjeev Sharma. Hello, I am Sanjeev. So this was a signal that I generated, okay, for this video, and as you heard, there were a lot of noises in that signal. Okay, so the problem is that I want to denoise the signal, or you can say I want to reconstruct this signal, provided I want to preserve the specific feature, that is my voice, in this signal. Okay, so let me show you how you can do this and in a very efficient manner. This is the first step of any problem. Like if you get any problem, or if you are working on any topic, then first step is to analyze the problem completely. Okay, don't just start writing hundreds of lines of code, okay, which is an obsolete way to do the things. Okay, so the requirement, as I told, preserve the signal, specific features like sharp transitions, human voice, or any feature that depends on the domain of your problem. Okay, what your problem is. Okay, and in this signal I want to reduce the noise. Okay, the noise content of the signal. So how can you preserve or how can you reconstruct a signal? Okay, so the need is to preserve the voice. Okay, so the first one is to preserve the features. Okay, the feature in the signal was my voice. Okay, so I need to construct a signal which approximately matches the sentences in that signal. Okay, and also I need to preserve my voice in that signal. Okay, so second thing is that I need to remove the noise. Okay, so I need some smoothing parameter in my objective function. Third one is remove very high peaks. Okay, very high peaks again leads to very high noise content or very sharp transition. Okay, it may be due to very large amount of noise. Okay, so I need a parameter which reduces or removes very high peaks. Okay, so need some parameter in objective. So three functions are: one is to preserve the feature, second was to remove the noise, and third one is to remove the high peaks. Okay, so how can you reconstruct a signal? Okay, for reconstruction, as I told, I need to have a signal that approximately matches my given signal. Okay, so how can I reconstruct a signal which matches given signal? So we can do this by minimizing the difference between the required signal and the actual signal that you get after processing, okay, or after solving an optimization problem. Okay, so consider that your desired signal is Z and your signal after reconstruction is Z cap. Okay, so consider that Z is your desired signal and Z cap is that you're getting after solving an optimization problem. Okay, so you're minimizing the norm of the difference between the two signals. Okay, so in this way you can get exact fitting. Okay, if this is your only objective, then you will get an exact fit which exactly matches the given signal. Okay, but the problem is we need to remove the noise. So here's a smoothing regularization. Okay, so consider this matrix S, which is an smoothing matrix. Okay, and multiplying this matrix S with vector Z cap is equivalent to taking the successive difference between the signal at time t plus 1 and the signal at time t, and add all such differences. Okay, so multiplying S with the vector Z cap is adding the successive differences. Okay, and your z cap is your variable, okay, is an optimization variable, okay, and it's an n dimensional column vector, okay, where n is 37650, okay. Here 37650 samples were taken for the signal, okay, but our first priority is to preserve the actual content of the signal, okay. So we will assign the highest priority to the difference between the two signals, okay. So here we will multiply this smoothing regulation with a scalar variable ls, okay. Ls is a multiplying factor for our smoothing regulation, okay. And now comes the magnitude regulation for removing the peaks, okay. So we will reduce the norm of z cap. We will assign a low priority to this magnitude regulation as well, that is lr is our multiplying factor, okay. So finally our problem reduces to minimize this function, objective function, over the variable z cap, taking the norm, relative norm of z minus z cap, and adding the smoothing regulation with the multiplying factor ls, and adding the magnitude regulation function which multiplied by scalar lr, okay. So s is nothing, just a smoothing matrix, and multiplication is equivalent to taking the difference of successive components. So let me show you the code of matrix S. So this is the code for generating the smoothing matrix, okay. Your input parameter is n, that is a dimension of a vector that is to be multiplied, okay, with this matrix S, okay. This is the dimension of this vector, and this is your output matrix, okay. Here you can take the code of this matrix, okay. This is the code for this matrix. I'm sorry about this h of z, it's not here, okay. So this is a code for matrix S. You can directly copy it and paste in your m file. You can create an m file for this, okay, and use it, okay. This is a code for generating matrix S, okay. It is nothing but just an equivalent of it's nothing but just multiplying your matrix S with your matrix z cap. Is just adding the successive differences of a signal, okay. This code was written by me for this problem, okay. You can use it freely, okay. So this is a final problem, and let me show you the output with lr equal to 0.08 and ls equal to 0.07, okay. And let me show you what it sounds like, okay. Hello, I am Sanjeev Sharma. Hello, I am Sanjeev. So as you heard, the noise was removed, but with little distortion to the signal, okay. So you can change these features lr and ls, and you can again work on this optimization problem, and you can see that setting these parameters lr and ls, choosing appropriate parameters, will improve the signal, okay. So guys, thank you for watching this video. I hope you enjoyed it. I presented here a way of preserving the features of the signal, okay, and providing you need to do some sort of denoising or reconstruction or something, okay. So you can use it anywhere, okay. You can use it in your projects, okay, changing parameters lr and ls. So thank you guys.